Today, we build a brain. Not a whole one, a genuinely small one, a few hundred numbers, trained by you, on your own machine in the next 50 minutes. And then, because this series doesn't do hype, I'm going to show you something most courses won't. On the actual problem we've been working on this whole time, that brain loses. Not to magic. To a one-line logistic regression from part 6. Stick with me, because understanding why is worth more than the neural network itself. Welcome to part 7 of AI and Machine Learning from Absolute Zero, brought to you by CloudNimbus. Demystifying, not dazzling, that's the whole agenda today. Here's what's ahead. A single neuron computed by hand, so you see exactly what's inside one. A real network, trained in PyTorch on our churn data. Backpropagation in plain English. The honest scoreboard against everything we've built so far. Then modern AI properly explained, tokens, embeddings, and what a transformer actually adds. A working and honestly limited semantic search engine. And the real difference between prompting, RAG, and fine-tuning. So you stop reaching for the expensive one when you needed the cheap one. A neuron does 3 things, and that's the entire unit, the whole building block behind everything from a 3-line toy to the largest language model on Earth. 1. Multiply each input by its own weight, a number saying how much that input matters. 2. Add them all up, plus one more number called a bias, a baseline nudge. 3. Pass the result through an activation function, so the output lands somewhere sensible for a probability that's usually a sigmoid, which squeezes any number, however large or small, into somewhere between 0 and 1. That's it. Weights, sum, bias, squash. That is the entire unit. Let's compute one ourselves. No training yet, just the mechanics. Take a brand new customer on a month-to-month contract, paying rather a lot. Feed those 3 facts through a neuron with weights we chose ourselves. Using plain intuition, long tenure should lower risk, so that weight is negative. A high bill should raise it, so that weight is positive. Run the numbers, squash the result, and out comes 92.8% churn probability. Now a long tenure customer on a 2-year contract, paying very little. Same neuron, same weights, different inputs. Out comes 12.5%. We picked those weights ourselves because we already understood the problem. Training a network is the machine finding weights like that on its own, the exact gradient descent from part 5, just repeated across many neurons at once, all their weights adjusted together, every single step. Put several neurons side by side, all looking at the same inputs, and you have a layer. Stack layers on top of each other, each one feeding the next, and that stacking is what deep learning actually means. Nothing mystical. Neurons, side by side in layers, stacked deep. So how does a network with hundreds or thousands of weights actually learn from one wrong answer? Backpropagation. After a prediction misses, you work backwards through the network, asking every single weight the same question. How much of that mistake was yours? Then you nudge each weight a little, in proportion to its own share of the blame. It's the same hill-in-the-fog idea from part 5's gradient descent. Feel which way is downhill, take a small step, repeat thousands of times, just applied all at once, to millions of dials instead of 1 or 2. The clever bit is doing that efficiently. Instead of nudging each weight one at a time and rechecking the whole network, backpropagation works out every weight's share of the blame in a single backward sweep. Nobody derives this by hand. PyTorch computes every one of those corrections automatically the instant you call one line. Loss.backward. Here's the actual network we trained. 45 inputs, every column of our churn data, one hot encoded and scaled, same pipeline as part 6. 16 neurons in the first hidden layer, 8 in the second. 1 neuron at the end, squashed into a churn probability. Notice the shape, 45, down to 16, down to 8, down to 1. Each layer is forced to compress what it learned into fewer numbers. And that compression is exactly what makes the network find a useful summary, instead of just memorizing every row. Count every weight and every bias in that whole structure, and you get 881 learnable numbers. Not billions, not even a million. 881, small enough to train on an ordinary laptop in seconds. Trained for 60 epochs, 60 full passes over the training data, and the loss fell from 0.720 down to 0.415. Same falling loss story as Part 5's from scratch regression. Just a deeper model doing the falling this time. Now the honest part, and I promise not to soften it. 3 models, same data, same split, same 5 metrics we've used all series. Part 6's logistic regression, 80.6% accuracy, 0.842 ROCAUC. Our brand new neural network, 79.7% accuracy, 0.839 ROCAUC. Gradient boosting, 79.3% accuracy, 0.835 ROCAUC. The neural network lost. Not by miles, these 3 sit within a single percentage point of each other, but it lost to a model that's 1 line of code and trains in under a second. It also took real design decisions to get there. How many layers? How many neurons per layer? How many epochs? What learning rate? The logistic regression asked for none of that. Here's the rule, and it's an honest, industry-standard finding, not a hot take. On small to medium tabular data, rows and columns of business facts, like ours, linear models and gradient boosting usually match or beat deep learning. Neural networks earn their keep on unstructured data at scale. Images, audio, language, data where a human can't handcraft the columns, because there simply aren't any obvious ones to craft. Nobody writes a grandmother's nose length column for a photograph. That's where depth pays for itself, and knowing when not to reach for it is as valuable as knowing how to build it. Let's use that same idea to properly explain modern AI without a single equation. Remember our network, 881 learnable numbers. A large language model is built from the exact same 3 ingredients: weights, sums, biases, activations, just an almost unimaginable number of them. Hundreds of billions of parameters instead of hundreds. Same idea. Vastly more of it, trained on vastly more text. First, tokens. Before a language model reads anything, your text gets chopped into pieces, roughly word-sized chunks, sometimes smaller. That's a token. Nothing more exotic than that. Second, embeddings. Each token gets converted into a list of numbers, an embedding, and the whole trick is that similar meanings land near each other in that space. Cancel and terminate end up close together. Cancel and aeroplane end up far apart. Meaning turned into geometry, so how similar are these 2 ideas becomes a distance you can actually measure. Third, what a transformer added on top of that. Attention. For every word, the model weighs how much every other word in the sentence matters to it, right now. The customer said the bill was wrong, so she cancelled it. Attention is what lets the model work out that it almost certainly means the bill, not the customer, by weighing every other word's relevance to that one pronoun. Doing that weighing, for every word against every other word, at enormous scale, is most of what separates a modern language model from everything that came before it. Let's build the simplest possible version of search your own documents, the retrieval half of RAG. 15 short customer support snippets turned into vectors using TF-IDF, which weighs words by how distinctive they are. Ask a question, turn it into the same kind of vector, and measure the angle between it and every document. That angle is cosine similarity. Ask something that shares real words with a document. How do I cancel my subscription? And it works nicely, scoring between 0.60 and 0.78 against the right answers. Now ask the exact same question, paraphrased, sharing no vocabulary at all with the document that answers it. How do I stop paying for this service? Every single score comes back 0.000. TF-IDF has no idea those 2 sentences mean the same thing. It only counts shared words, and there aren't any. Picture that inside a real support chatbot. A customer types exactly that question. The correct answer is sitting right there in the documents, and the system tells them it found nothing. Not because the model is unintelligent, because word counting was never going to understand paraphrase, no matter how well you tune it. That failure is the entire argument for embeddings, a proper sentence embedding model, trained to place similar meanings near each other rather than similar words, would catch that paraphrase instantly. And the upgrade from here is one import. Swap the word counting vectorizer for a sentence transformer model, and every other line of this search engine stays exactly the same. Last piece of vocabulary, and this is where I see the most money wasted. 3 tools, 3 very different jobs. Prompting, just ask a general-purpose model well. Use it when the knowledge is already inside the model, general facts, general writing, general reasoning. No training, results in seconds, and it solves most real tasks. Always try this one first. RAG, Retrieval Augmented Generation. Exactly what we just built the skeleton of. Use it when the model needs your documents, your company's policies, this week's inventory, a customer's own account history, and those documents change often enough that retraining on them would be absurd. Fine-tuning. Actually retraining part of a model's weights on your own examples so its behavior itself changes. A consistent tone, a strict format, a specialized judgment call, repeated reliably across huge volume. Not for new facts, for new habits. Here's the expensive mistake I see constantly. Teams reach for fine-tuning when what they actually needed was RAG. They want their chatbot to know this week's return policy, so they try to bake it into the model's weights, instead of simply handing the model the policy document at question time. Fine-tune, and the moment the policy changes next month, you're retraining all over again. Retrieve instead, and you just update the document. The model reads the new version on the very next question. Try prompting first. Reach for RAG when the facts are yours and they change. Save fine-tuning for when the behavior itself, not the facts, needs to change. Hands on keyboards. Open the Part 7 notebook. It runs entirely offline once the churn file's downloaded. No waiting on any external model downloads. Run the hand-built Neuron yourselves and watch both probabilities land, 92.8%, 12.5%, before you've trained a single weight. Build the network, print 881 learnable parameters, and watch the loss fall over 60 epochs on your own screen. 0.720 at the start, down near 0.415 by the end, the same falling curve every time, because the random seed is fixed. If PyTorch won't install in your environment, the notebook has you covered. MLP classifier from scikit-learn is a real neural network too, and it trains on the exact same prepared data with no separate framework required. Build the honest scoreboard yourself, and confirm logistic regression still edges out the network you just trained. Run the search engine, ask it the fair questions, then ask it the paraphrase, and watch every score collapse to 0 live on your own machine. There's a ready-to-run upgrade to a real sentence embedding model in the notebook too. It needs an internet connection this offline lab doesn't have, but it's the exact code you'd run in Colab. One import away from fixing everything we just watched fail. So what do you own now? What a neuron actually is: weights, sum, bias, squash, and nothing more mysterious than that. Backpropagation in one sentence. Work backwards, ask each weight how much blame is theirs, nudge accordingly. The honest finding that deep learning doesn't automatically win, and exactly when it does. Tokens, embeddings, and attention properly explained with no equations required. And the real difference between prompting, RAG, and fine-tuning. 3 separate tools for 3 separate jobs, not 3 words for the same thing. Homework. 1. Add a third hidden layer to the network and retrain. Does accuracy improve, or does it just hand the model more room to overfit on data this size? 2. Write 2 of your own paraphrased queries for the search engine and confirm TF-IDF fails both, for the same reason it failed today. 3. Take 3 real scenarios from your own work or life and decide out loud for each one, prompting, RAG, or fine-tuning. Say your reasoning aloud, not just your answer. That's the actual skill. The notebook's linked below, solutions included, once you've actually tried. Part 8 is the capstone. Every single piece from parts 4 through 7, the clean data, the tuned pipeline, everything we've built, comes together, gets wrapped in a real web app, and goes live on the internet with a URL you can put in front of a recruiter. No new theory, just assembly and shipping. Subscribe so it finds you, and the full guided course with graded exercises is on Udemy through CloudNimbus. Everything's linked below. You built a neural network today, and you know exactly when not to use one. That's rarer than it sounds. I'm Rohan Singh, this has been CloudNimbus, and I'll see you in Part 8.